Hello, my name is May, and today I'd like to share with you some of the low latency streaming work that we have been doing in our research group. One area that we actively work on is developing solutions that provide more accurate bandwidth tracking and prediction in low latency streaming applications. Because of this low latency scenario, our solutions are also designed to work well with the CMAF's CTE standard, which stands for Chunk Transfer Encoding. Our solutions also cover other aspects such as the ABR and the playback rate control components, which we'll discuss in greater detail later on. A quick overview of the timeline of our work. We started working on an ABR for CTE in early 2019. The solution is known as ACT, and one of the key contributions here is our bandwidth measurement module, designed specifically for the CTE pipelines, since existing throughput measurement method of dividing the segment size by download time would not work well under CTE scenario. So after that first iteration, we continued to refine the ACT bandwidth measurement module to produce even better results in our subsequent papers, which includes LOL and also LOL+. For LOL, which was submitted to ACM MMSIS 2020, we were also awarded the runner-up prize by the challenge organizer Twitch. First, a quick summary of the said challenge. Mainly, the solutions in this challenge need to achieve near-second latency while balancing other QoE factors such as high quality, little rebufferings, and little switches. Our multi-component solutions are designed based on well-known low-latency streaming principles and standards such as HAS, CTE, and adaptive playback strategies. This is an architecture overview of our LOL and LOL+ solutions, and I'd like to highlight the three main components. First, the throughput measurement module, the bitrate selection module, which implements a learning-based ABR algorithm, as well as the playback speed control module. And finally, the two auxiliary components known as the weight selection and the QoE evaluation modules. They mainly support the ABR algorithm in bitrate selection. First, we introduce our throughput measurement module. As mentioned earlier, CMAF's CTE standard aims to reduce latency for live streaming, but also introduces a problem with existing throughput measurement methods due to the presence of interchunk idle periods. To visualize this problem, we look at this scenario where the chunks of a segment are generated with idle times in between, such as an idle time as seen between chunks 5 and 6 over here in this diagram. These idle times, if we factor them in the segment download time, this would cause a wrong estimation of the segment download throughput. Hence, to fix this issue, we can see that instead of measuring download time at a segment level, we need to identify the actual chunk download times as annotated in red over here. So in LOL and LOL+, we propose a two-stage algorithm that uses the latest fetch API to improve over ACT. In the first step, the chunk boundary identification, the algorithm identifies the beginning and end times of each chunk download by capturing the move box in fragmented MP4 data. This is enabled thanks to the fetch API, and hence our algorithm is able to use the streaming response body object, which allows us to track the progress of chunk downloads and parse the chunk payloads in real time. And in our second step, chunk filtering, we drop the first and last chunks to avoid any transient outliers. For our learning-based ABR algorithm, we adapt from the idea of self-organizing maps, or SOM in short. I'll explain the high-level intuition of the algorithm here, and further technical details can be found in our paper. So first, the map is initialized with 3 neurons, which represent the 3 available bitrate levels as in our setup. In the first step, we select the neuron that is currently closest to what we call the optimal state, which is a point on the feature map. This optimal state is determined based on the current throughput, our target latency, buffer, and QoE values. So let's say the optimal state is this state over here with the orange outline. Hence, the closest neuron is the leftmost neuron, annotated as 1 over here. In the second step, we update the selected neuron to move closer to the optimal state. This is a standard SOM mapping step to reward the winning neuron, also known as competitive learning. We then retrieve the next segment at the bitrate level represented by the selected neuron. In the third step, after the segment is retrieved and played back, we update the neurons again to learn from our past decision. We first identify our consequent state, based on the current latency, buffer, and QoE resulting from the previously selected bitrate. We then move the selected neuron closer to it. So for example, let's say our previously selected neuron did not do very well, and the consequent state is very far from our optimal state, like the state over here with the blue outline. Then the neuron will be moved away from the optimal state and will be less likely to be selected in subsequent cycles. So these steps are repeated each time we need to select the next bitrate, which is typically at every segment download boundary. Next, we introduce our playback control module. The goal here is to adapt the playback speed to reduce latency while not risking rebuffering. For example, too fast playback speed can quickly bring down latency, but also deplete the buffer very quickly and risk rebuffering. Over here, we use a heuristic-based approach with configurable parameters. This table provides a worked example. First, the system predefines a safe buffer level, target latency, and allowable playback speed range. And let's say we have these three scenarios with different buffer level and latency values. In the first scenario, if the current buffer is less than the safe buffer level, then we would slow down the playback rate to avoid rebuffering. So we always check for the buffer first. And if the buffer is safe, such as in scenario 2 and 3, then we would look at the latency part. In scenario 2, if the current latency is less than the target value, then we would slow down the playback, which is good for building up the buffer so that if the latency starts to grow above the target latency, as seen in scenario 3 over here, then we would speed up the playback so that we can quickly bring the latency down. We implemented our solution in Dash.js and our code is publicly available on GitHub. We also did extensive evaluations of our solutions against other low latency solutions that also won the Twitch challenge. And the results of evaluating LOL Plus against its predecessor LOL, as well as the other low latency solutions, namely L2A, Stallion, and Dash.js Dynamic, are shown over here. We compare the three key metrics, average bit rate, rebuffering duration, and average latency, achieved by each of the solutions across the 11 network profiles. The green area here represents improvements that LOL Plus has made over the respective solutions. So we can see that when comparing LOL Plus against LOL and L2A, namely the blue and red graphs, we can see significant improvements in rebuffering duration, as well as some improvements in latency. The trade-off in bitrate is less significant, and our results also showed that this can be mitigated with higher target latency values, such as 2 or 3 seconds instead of 1 second. And when comparing against Stallion, LOL Plus has achieved improvements in all three key metrics. As for the playback speed control module, recall that ours is a hybrid-based method that used both buffer and latency in our heuristic, so we evaluated that against the latency-only and buffer-only equivalents, with the former being the Dash.js default implementation. Our results showed that we managed to reduce rebuffering duration significantly, up to 60%, along with minor improvements in latency as well. To understand the behavior of these three implementations, we can look at the graphs above that plot a sample run for each of these implementations. For the first one, the latency-only implementation, the playback speed, i.e. the red line, increases along with the latency and starves the buffer tremendously, as you can see over there. Whereas in the second and third graphs, which is the buffer-only and our hybrid implementation, we can see that playback speed is more helpful in maintaining a healthy buffer, and more importantly in the third graph, our hybrid method can help to quickly bring the latency down once the buffer recovers, as seen here between segment number 70 and 90. Alright, thank you. This marks the end of our presentation. Again, our code is available on GitHub and our paper is also available, so please do check them out and feel free to reach out to us if you have any further questions.